All right, welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us soon to be Dr. Devansh Jalota, who is a PhD candidate in computational and mathematical engineering at Stanford University. Devansh works on data-driven learning algorithms and incentive schemes to advance science and practice of market design for sustainable resource allocation. And particular applications are in future mobility systems and electricity markets. Although his young age, he has already been recognized by a number of awards, including a fellowship from Stanford and some Informs awards. Also notably, that's not in his bio, but some of his work has been featured in fancy newspapers like New York Times that I found very cool. Prior to joining Stanford, he received a bachelor's in applied mathematics and civil engineering at UC Berkeley. So Devansh is on the job market, and I really like his work, and that's why I asked him to come and enlighten us with this talk. And today's talk is going to be about algorithm incentive design for sustainable resource allocation beyond classical fission markets. So, as I said, I'm very happy to hear more about it, and without further ado, I give you the stage.
Thank you so much, Joyle, for the very kind introduction and also for this invitation. So I'll get started in talking about this particular work, where I'll specifically be focusing on, as Joyle mentioned, on algorithm and incentive design for sustainable resource allocation, where I'll specifically be focusing on going beyond classical Fisher markets. So just to set out some context, we very much live in a resource-constrained world, be it the limited access to energy resources, the limited availability of road space, which often leads to quite poor traffic congestion outcomes, or even the limited availability of vaccines during the pandemic. While these applications are quite diverse, they very much raise the same fundamental economic question, which is how do we best allocate our available set of limited and scarce economic resources across the population, potentially when we have strategic agents that are trying to maximize their individual objectives or utilities within the system. And the age-old economic answer that we've come up with to this particular question has been the design of market mechanisms, which typically involves setting the rules of the marketplace. For instance, we are designing some form of a pricing-like mechanism to make sure that the right resources end up with the right groups of people while we align the incentives of the agents within the market. And indeed, market mechanisms have made their ways into our everyday lives across a wide range of applications, and in particular for the three applications I mentioned on the previous slide, where electricity markets are often used to allocate energy resources. Congestion pricing on roads is often used as a mechanism to reduce traffic congestion on roads, as well as a wide variety of vaccine mallocation mechanisms were adopted during the course of the pandemic. And moreover, recent advances in computing and the proliferation of data have only opened up many new avenues for designing market mechanisms in practice, right from online advertising to a wide range of new marketplace platforms such as Uber, Lyft, and Amazon, as well as more recently, even in a range of smart mobility contexts with the advent of connected and autonomous vehicles. Now, while the proliferation of data and advances in computing have offered us a lot of new opportunities for designing market mechanisms, and in particular improving the allocation efficiency of market mechanisms in practice, they've also introduced a wide range of new challenges in the design of such mechanisms for resource allocation. For instance, market mechanisms typically geared towards efficiency maximization objectives, such as congestion pricing for traffic congestion mitigation, often end up raising quite serious fairness and equity concerns, and hence might often remain even unimplemented in practice. Moreover, beyond fairness and equity concerns, data, while having the potential to improve the allocation efficiency of resources, is often plagued with uncertainty, and moreover can raise quite serious privacy concerns that often render existing mechanisms that typically rely on having access to complete information on user preferences as often completely inadequate for a wide range of decision-making contexts within resource allocation settings. And finally, the abundance of data also enables the easy strategic manipulation or gaming of information, which also leads to a new set of security challenges. So overall, given the wide-ranging nature of some of these challenges, there's really a need for us to shift from our traditional worldview of designing market mechanisms, typically focused on efficiency maximization outcomes, to now incorporating a variety of these new societal considerations in the design of market mechanisms for resource allocation. And what's interesting about incorporating several of these societal considerations is that they often introduce a range of new technical challenges. For instance, fairness and security concerns may often introduce new constraints over the allocation of resources, under which computing the optimal resource allocation strategies or the resulting equilibrium outcomes may often become intractable. With regards to privacy and uncertainty, often complete information on user attributes is really necessary for market mechanisms to really be effective. However, we might not really have access to such information under privacy and uncertainty related concerns. So consequently, what we really need are new tools and methodologies to really be able to overcome several of these new technical challenges that are associated with incorporating these different societal considerations in the design mechanisms for resource allocation. And with this backdrop, this really brings me to the core focus of some of the research that I've done during my PhD, which has been predominantly to leverage tools from operations research, computer science, and economics to be able to advance both the science and practice of market design for sustainable resource allocation. Within my work, I operate within this broader view of social sustainability, where we're not just only interested in efficiency maximization outcomes, but also interested in these other societal considerations such as fairness, security, and privacy in the design of such market mechanisms for resource allocation. And in particular, in my work, I pursue two key research thrusts. The first is more foundational and methodological, wherein I seek to take a variety of these societal considerations, be it fairness, security, or privacy, into classical resource allocation models and develop new tools and algorithms for decision making in these often more complex settings, specifically to address several of the key technical challenges I laid out on the previous slide. In my work, I've developed both optimization-focused methodologies as well as data-driven and online learning algorithms. And the key unifying feature across my research from a methodological perspective has been to use tools from game theory and market design, which are really critical and necessary to be able to capture the different strategic interactions and the incentive structures of various stakeholders that are typically involved in these resource allocation applications. The other key research thrust that I pursue is more on the application-driven front, wherein I seek to take several of these theoretical advancements to a variety of important societal applications, which have in effect also influenced my methodological developments as well. And in terms of applications, the specific application area of interest for me has predominantly focused on future mobility or transportation systems, as well as I have some other work in other areas, including electricity markets, as well as a range of settings where now artificial currencies are becoming increasingly prominent in our daily lives. So overall, with this backdrop of my research, here's just the agenda for the rest of the talk. So I'll just start by giving out some key highlights from some of the work that I've done during the PhD along the three different lines of sustainability, that of fairness, security, and privacy. And of course, you can find more details at my website. And then I will deep dive into one specific project, which will be the main focus of this talk, on online pricing in Fisher markets. And of course, please feel free to interrupt at any point if you have any questions. Okay. So let me start by just talking about some of the key highlights of my research, where I'll start by focusing on the first aspect of sustainability, which is that of fairness and equity, wherein a key aspect of my work has been focused on addressing the equity concerns of congestion pricing. So just to set out some backdrop, congestion pricing, as you may know, is very much a promising strategy for traffic congestion mitigation, wherein the key idea is that we set tolls on roads so as to reduce the overall traffic volume passing through the roads and thereby potentially improve the overall congestion outcomes within the system. However, a key aspect that congestion pricing has really faced issues with regards to deployment in practice has been the resulting fairness and equity concerns, wherein congestion fees have often been described as imposing a tax on the working class. And given its regressive nature, it is met with a large amount of negative public attitudes towards the deployment of congestion pricing in practice. So consequently, what some of our work has focused on has been trying to challenge this long-standing view that congestion pricing necessarily exacerbates income inequality by developing new tools and methods that somehow balance between these different objectives of sustainable transportation, that of efficiency, which is to reduce traffic congestion, while also getting some desirable fairness or equity-related properties. So just to give you a flavor of how we've thought about balancing these different objectives of fairness and efficiency through congestion pricing, in one particular work, we studied a problem called the unfairness constrained traffic assignment, where the key idea here is that we want to solve the following problem, where we're minimizing over all feasible flows within the traffic network, the total travel time within the system. And we want to do this while satisfying certain fairness constraints, which essentially just bounds the worst case ratio of the travel times of users within a given system, which essentially ensures that the worst off users in the system don't have more than beta times the travel time as any other user that is using the particular transportation network. So essentially what this problem is doing is we're trying to maximize efficiency or minimize the travel time in the system while satisfying certain fairness constraints to be able to balance these objectives of efficiency and fairness in traffic routing. And it turns out that solving this problem ends up being NP hard, primarily because of the non-convexity of the unfairness constraints that we've introduced within this problem to satisfy certain fairness criteria that we might desire within the system. So given the hardness of solving this particular unfairness constrained traffic assignment problem, what we do within this work at a very high level, which I'll just describe, is we introduce a computationally tractable convex programming relaxation of this NP hard problem, which we call the interpolated traffic assignment problem, wherein we drop these non-convex unfairness constraints and instead modify our objective to one that just takes a convex combination of two different objectives, which is an efficiency promoting objective and a fairness promoting objective. And by taking this convex combination, our hope is that we can try to get the best of both worlds, that is the efficiency gains of the efficiency promoting objective and the fairness gains of the fairness promoting objective, and thereby get a good solution to the unfairness constrained traffic assignment problem that we originally wanted to solve in a very computationally tractable manner. Now, it raises the following question now that we've come up with this particular approximation called ITAP, which is how good an approximation is it really to the original NP-hard problem that we originally set out to solve? And it turns out that we can establish several theoretical bounds on the resulting solution fairness and efficiency, which is to actually demonstrate theoretically what the bounds in the performance of our interpolated traffic assignment problem are relative to the original NP-hard problem that we originally wanted to solve, as well as we can also test the performance of our algorithmic approach numerically when we can compare our algorithm to a range of benchmarks on a variety of different real-world transportation networks. So that's pretty much how we deal with it at a very high level in terms of addressing the problem of how good an approximation is ITAP to the original problem that we wanted to solve from both a theoretical and numerical perspective. However, it still leaves open the following very key and important question, which is that even though ITAP is a good solution to this original NP-hard problem, can we actually implement the proposed routing policy that is being recommended by ITAP in practice? And therefore, this really involves devising some form of a congestion pricing scheme to implement the particular routing policy we have computed in practice. And it turns out that because of the specific structure of this interpolated traffic assignment problem that we've constructed, it in fact yields a very natural class of congestion pricing schemes, and in fact results in the first set of congestion pricing schemes that have been developed for fare routing in the context of general road networks. So overall, just to sort of go back on this point, essentially this particular work that I just presented to you of developing this convex programming relaxation for this fairness constrained traffic assignment is very much just part of my broader agenda on addressing equity issues in congestion pricing, which is actually an area we've explored in a variety of different ways. For instance, in another work, we study congestion pricing, not just from the lens of tolling roads, but also from the lens of can we use the collected toll revenues potentially by giving refunds to the right groups of users. And in fact, within the game theoretic frameworks that we study within that context, we can show that we can provably improve system efficiency, which is reduce traffic congestion, without worsening the level of wealth inequality within the system if we devise these revenue refunding schemes appropriately. In more recent work, we've also developed game theoretic frameworks to provide policy insights regarding the optimal design of a variety of recent equitable congestion pricing implementations that have started to take place within the Bay Area, namely that of credit and discount-based congestion pricing mechanisms, which are designed to provide subsidies to low-income users such that they can access tolled roads. So overall, to summarize, my work on addressing the equity concerns of congestion pricing largely uses these key tools of optimization and game theory, as we're not just interested in computing these computationally tractable policies to route traffic within the system that satisfy these fairness or equity criteria, but also combine that with congestion pricing schemes to actually ensure that we can actually implement the routes that we have recommended in practice. And what I'd really like to emphasize about this particular line of work is that much of this has actually been done in collaboration with real stakeholders. And in particular, a key collaborator during some of our projects was from the US Department of Transportation. Okay, so that was just a quick overview of some of the work on the first aspect of sustainability, that of fairness and equity. So I'll now move to the second aspect of sustainability, which is that of security, for which I'll be a bit more brief. And in particular, in the context of security, the key focus of some of my work has been to make fundamental algorithmic contributions to a range of equilibrium computation problems that tend to arise within security games. And in particular, in one of our works, we provided the first set of algorithms for which we have provable performance guarantees for this very general class of security games known as multi-resource Bayesian Stackelberg security games. Now, while I'm happy to go into more details on the exact definition of this class of games offline, what I would like to mention here is that we've been able to apply some of the theoretical results we have within this work to practical data sets through a collaboration with Stanford University's Department of Public Safety, which is in charge of enforcing parking regulations on Stanford's campus. And in particular, we've been able to demonstrate the efficacy of some of the algorithms that we've developed on Stanford's parking enforcement data in terms of increasing parking revenues relative to the status quo parking enforcement mechanism currently in place on Stanford's campus. So finally, having talked about the first two aspects of sustainability, which is that of fairness and security, for the purposes of today's talk, I will focus on the third aspect of sustainability, which is that of privacy and uncertainty. And in particular, I will focus on addressing the privacy and uncertainty concerns in the context of a classical framework for fair resource allocation, which is that of Fisher markets, which is actually only a framework I came across when doing some of my work on other transportation focused applications. The work I'll present is joint with Yinyu Ye. And the reason I'm very excited to talk about this work is that it very neatly combines several of my key methodological areas of interest in that it not only uses tools from optimization and data-driven and online learning to be able to design and analyze the algorithms that we develop, but it also uses pricing mechanisms to ensure that we can actually implement the outcomes that we desire in practice. And also, I'll mention that the tools and techniques that we've developed in this work are actually quite general purpose, in that we've also been able to apply similar techniques to, for instance, learn optimal tolls in the context of transportation networks. Okay, so with that, I'll move on into the second part of the talk, which will be the main focus, where I'll deep dive into this particular paper. And to talk about this, I'll start by just introducing the Fisher market framework and its associated uncertainty and privacy limitations, go in to a review of the literature, talk about the model and the algorithms that we develop, and finally conclude. So let me start by first introducing the Fisher market framework. So what do we have in a Fisher market? We have agents, we have resources, and we have a certain price, PJ, that is imposed on each of the resources. I will assume that agents have linear utilities over resources. So UTJ is the utility of an agent for 1 unit of a resource, and X is the amount of the resources that are consumed. So the amount of the utility accrued by the agent is just going to be U times X. Now, a key and fundamental assumption in Fisher markets is that all buyers have a certain budget, WT, within the market. And given this budget, we can define a so-called individual optimization problem of agents, where they're trying to maximize their utilities while satisfying the budget constraints that they have within this market. And then, given this individual optimization problem of agents, the fundamental problem we're interested in solving in a Fisher market context is that given that all resources have some capacity CJ within the market, how do we find the right prices in the market to match supply with demand? That is, how do we get an equilibrium or a market clearing outcome? Now, it turns out in a Fisher market context that if all buyers are solving this individual optimization problem that I've laid out on this particular slide, then in fact, very beautifully, we can compute the equilibrium prices within the market by just solving a global convex program, which I will refer to as a social optimization problem. So I'll just briefly introduce the social optimization problem. The way it proceeds is that we're trying to maximize the sum across all agents of their budgets times their log utilities, while satisfying the capacity constraints of the resources within the market. And the fundamental and beautiful result here is the following, that if we set the prices in the market to be exactly equal to the dual variables of the capacity constraints of the social optimization problem, then these are exactly the prices that would correspond to the equilibrium prices at which supply would match demand. That is, the optimal solutions of the two problems would be equal if we set the prices to be the dual variables of these capacity constraints. Now, just a few quick notes on this particular social optimization problem. So this problem is often referred to as the Eisenberg-Gale convex program, behind the two researchers that first discovered this result and introduced this particular convex program back in 1959. And moreover, what's very nice about this particular social optimization problem is that it can actually be shown to be solved in polynomial time, which means that we actually have a very efficient algorithm to be able to compute equilibrium prices within the market, which is of course not true for general equilibrium computation problems. And finally, what's also very nice about this particular social optimization problem is that because we have a logarithmic objective, as we have here, it accompanies with it certain very nice fairness related properties. For instance, that all users are actually guaranteed to obtain at least some resources within the market, which is guaranteed because we have a logarithmic objective that we have here within the social optimization problem. So given some of these very nice computational as well as fairness related properties with regards to Fisher markets, they've actually started to find a wide range of applications, both within the tech industry across a wide range of contexts, as well as in a range of other social good applications, from food allocation systems to public decision making, and even the allocation of computing resources within a university cluster. Now, while Fisher markets have found these wide range of applications, I would still say that the applicability of Fisher markets may yet be quite limited for a wide range of other applications that we might possibly be interested in. So in particular, to see this, if we think about how we're computing equilibria by, let's say, solving this Eisenberg-Gale program, as I have on the slide, then what we realize here is that to be able to compute equilibrium prices by solving this problem, we need complete access to information on buyers' budgets and their utilities. However, we might not really have access to that information in practice, for instance, because of privacy and uncertainty related concerns. And moreover, an implicit assumption within Fisher markets is that all transactions are somehow taking place in a static market where all buyers are present within the market simultaneously. However, in many real-world markets, we typically have an adaptive or a dynamic component where buyers are often sequentially arriving into the market over time. So given some of these key limitations of classical Fisher markets, this really brings me to the key contributions of this work, where we study a new online incomplete information variant of Fisher markets. Specifically, we study a model where buyers arrive into the market sequentially over time with budgets and utilities drawn IID from some distribution. For this new Fisher market model, we first study the simplest class of pricing policies, namely that of static pricing, where we set exactly the same price for all users within the market. And we show that static pricing, which is really what equilibrium pricing is really all about, has serious performance limitations within this online market model that we study. Given the limitations of static pricing, we then develop adaptive pricing approaches for which we can get significantly improved performance guarantees, both in the setting where we have access to the distribution of users as utility and budget parameters, as well as in the setting where we do not have access to that distribution. And what I'd really like to emphasize here about the class of adaptive pricing mechanisms that we develop, they're going to be so-called posted price mechanisms, where we set prices and see how much buyers consume given the prices that are set. And these posted price mechanisms will satisfy two key properties. So first, they're going to be data-driven in that they can use sequentially revealed observations of users to be able to update prices, which is something that static pricing was, of course, not able to adapt to. And secondly, by focusing on posted price mechanisms, we're able to capture scenarios where utility maximizing agents are able to consume their optimal bundles of resources within the market, which is really how real markets would typically tend to operate, focused on posted pricing. And then finally, towards the end, I'll mention briefly about some extensions as well as some experimental results. Okay, so let me now move into talking about the related literature. So of course, we're not the first to study incomplete information variants of Fisher markets where we don't have complete access to information on buyers' utilities and budgets. However, much of the prior work in this regard has largely focused on the regime of distributed algorithms, which typically focuses on a setting where buyers typically arrive into the where buyers typically repeatedly interact within a static market in this multi-round game until we converge to some notion of equilibrium prices within the market. And now there have been many approaches that have been developed for the study of distributed algorithms, including a new class of methods based on alternating direction methods that we introduced within a separate paper. However, the focus of this work is on the regime of online algorithms, wherein buyers, rather than repeatedly interacting in the market, are arriving sequentially into the market one by one over time, which typically mimics the setting where users may often not be present all at once within a given market. Now, of course, the setting of online user arrivals has also received a lot of attention within the literature, particularly in the context of online linear programming and online convex optimization. However, much of this literature is focused on objectives that we're trying to optimize, which satisfy these properties of being bounded and non-negative, which are really crucial to be able to analyze the performance of those algorithms within those settings. However, within the Fisher market setting that we're studying, if you recall, we're trying to optimize for this particular logarithmic objective. And so consequently, our objective clearly does not satisfy these properties of being bounded and non-negative. And so consequently, while the algorithms that we're going to design will be inspired by much of the existing literature, we're going to really need new techniques and tools to be able to extend some of the analysis for the bounded and non-negative objective setting to this more fairness promoting Fisher market setting that we're studying within this work, for which we have this logarithmic objective. And in particular, we develop a novel potential function argument, as well as leverage some tools from parametric optimization. Okay. And finally, there's also some prior work on online variants of Fisher markets. However, much of the prior work in this regard has largely focused on the setting where the agents are fixed and it's the goods that arrive online. However, our work is studying a setting where the goods are fixed, but it's the agents that arrive into the market over time. Okay, so with that, I'll now move into describing the model and talking about the limits of static pricing. So let me start by introducing the model. So we have resources with certain capacity Cj, and at each step, we're going to impose certain price Pt on the resources. And then within our framework, we have sequentially arriving utility maximizing agents. So an agent will arrive at a given period T with some utility and budget realization from some distribution. And on observing the prices, the agent will just solve its individual optimization problem to consume its optimal or utility maximizing bundle of resources given the prices that it observes within the market. Now, within this framework, what is our goal as a market planner? It is to devise some potentially data-driven pricing policy pie, which is just a sequence of prices for the end users within the market, based on some sequentially revealed data of users that is being revealed to us over time within the system. Now, what is the information that we can use to set prices and update prices at each step within the market? So within this talk, I'm going to assume two key pieces of information. The first is going to be access to the distribution on users as utility and budget parameters, which is just a quantity that is exogenously given to us at the beginning of the algorithm. Okay, and this is what one of the algorithms we're going to design is going to leverage. The other key piece of information is going to be what is really sequentially revealed to us over time, which is going to be just past observations of user consumption of all the previously arrived users within the market. Okay, so these are going to be the two key pieces of information that we will use to set prices at each step within our algorithm. I would like to mention that we could have, rather than thinking of a pricing-based policy, also have thought of our problem from the perspective of each time a user arrives, we observe their user attributes and use that to give them certain allocations within the system. And this is typically the setting that is studied within the literature. However, within this work, we really wanted to focus on designing posted price mechanisms because they're far more representative of reality, wherein utility maximizing agents are able to consume their optimal bundles of resources rather than just accept some allocation that is possibly given to them, as would happen under allocation-based policies. So now, given that we're studying these posted price mechanisms, a key question is how good are our posted price mechanisms really doing? And we're going to evaluate the performance of our posted price mechanisms on two key performance metrics, that of regret and constraint violations. So I'll start by introducing the notion of regret, which is just the standard notion of an optimality gap of an algorithm, where we'll measure regret by the difference between two terms, which is what is the optimal offline objective that I could have achieved on my Eisenberg-Gale program or social optimization problem had I complete access to buyers as utilities and budgets, compared to what is it that I do achieve with the online policy that we've devised. And we'll just take a difference of the two. A few quick notes on the regret metric. So we're studying regret with respect to this logarithmic objective because it is really equivalent to optimizing this logarithmic objective corresponds to finding equilibria within offline Fisher markets, as I mentioned earlier, as well as this logarithmic objective accompanies with it several desirable properties, for instance, with regards to fairness, that other possible objectives such as utilitarian welfare may not be able to buy us. So that's the first metric, which is that of regret. The other metric I'm going to use to evaluate the performance of an algorithm is going to be that of constraint violations. So I'll allow for some slack in violating our capacity constraints of the resources to be able to achieve good regret. But towards the end of this talk, I will mention that we can actually modify the algorithms to not violate the capacities while still achieving good regret. But this will help us greatly simplify the exposition by allowing constraint violations for now. Okay. The way we'll measure constraint violations is just the difference between how much of the resources are consumed under our algorithm compared to the available capacity of resources, and we'll just take an expected norm of that constraint violation. Okay, so these are going to be the two key performance metrics that we will use to evaluate how well our algorithm is doing within this particular Fisher market setting. Okay, so let me now move into talking about our results. And the first key result that we're going to look at is going to be studying static pricing algorithms which set exactly the same price for all users within the market, which is really what classic equilibrium pricing is really all about. And here's the key result. So take any static pricing algorithm, even one that has access to the distribution of users' utility and budget parameters, then it'll either incur a regret or a constraint violation that will be at least on the order of square root n, where n is the number of arriving users within the market. So what this result is essentially saying is that if we just restrict ourselves to static pricing policies within this online Fisher market that we're studying, then we have a lower bound in the performance of square root n that we cannot breach if we were just to restrict to static pricing. And this really suggests that we really need to think about shifting from our traditional paradigm of equilibrium pricing, where just a single uniform price vector applies to all users within the market when we're dealing with these online market contexts as we're studying within this work. And this really motivates the following very natural question that given the limitations of static pricing, can we possibly develop adaptive, maybe even data-driven pricing algorithms that use sequentially revealed observations of users to be able to update prices, which is something that static pricing was not able to do, and then maybe get us better or improved performance guarantees. So in the next, yes,
There is a question from Alice. I was waiting for the right moment. Do you assume that consumers do not have intertemporal preferences, for instance, trying to game the systems by getting resources cheap?
Yes. So yes, that is absolutely an assumption within this market. Yes. Yes.
Okay.
Yeah. Thanks for the clarification.
Thank you.
Yeah. Great. Okay. So now I'll move to this next part of the talk where I'll try to answer this question by essentially talking about the algorithms that we develop. Which are going to be adaptive. And I'll start by describing the algorithm, which I will refer to as the adaptive expected equilibrium pricing algorithm. This one is going to rely on access to the distribution of users' utility and budget parameters. So to talk about this algorithm, I will start by first talking about where is it that static pricing fails, even if we knew the distribution of users' utilities and budgets. And to see this, consider the following simple example. Let's say we have two goods, each with a capacity of n resources within the market. And we have two types of agents. Agent type 1 only has utility for good 1. Agent type 2 only has utility for good 2. And both these types of agents have equal arrival probability within the market. Now, it's straightforward to show that if all buyers have a budget of 1 within this market, then the static prices that we would set if we had access to the distribution of users as utilities and budgets would just be a half and a half within this particular market. And then, because both buyers have equal arrival probabilities, while n over 2 users of each type will arrive into the market in expectation, by the central limit theorem, the actual realized arrivals of any given type of users will deviate by the order of square root n. And this is essentially what's going to give us that the capacity violation of setting static expected equilibrium prices, even if we had access to the distribution, would give us a capacity violation that is going to be on the order of at least square root n. So given this exact limitation of static expected equilibrium pricing, where we over or under consume resources by this order of square root n, as I demonstrated to you, we're essentially going to try to overcome this exact problem to develop our adaptive pricing algorithm by just dynamically adjusting the prices of the resources that have been over or under consumed at any given point in time during our algorithm. And in doing so, our algorithm will be able to combine learning based on sequentially revealed user data with decision making to make better pricing decisions for subsequent users within the system. So I'll just very briefly describe how our algorithm works through the following very simple example. So let's say we have the same example as earlier with these two resources with 100 units each. And let's say we have 100 users within the market. So the average amount of resources per user given by this vector D is just going to be 1 because we have 100 units of resources and 100 users. Then the first thing that we will do to initialize this algorithm is going to be solve a certainty equivalent problem to set a price of a half and a half for both the resources within the market, as we saw earlier. And this can just be done by just solving a certainty equivalent problem, but that relies on this average capacity vector D that I mentioned. Now, let's say that during the algorithm, the first user that arrives is a user of type 1, which only has utility for good 1. Now, what this user will do is it will consume its utility maximizing bundle of goods. So at a budget of a 1 and a price of a half, it'll consume 2 units of good 1. So what we're left with after the arrival of the first user is 98 units of good 1, but 100 units of good 2. So somehow we've overconsumed good 1, but underconsumed good 2 at this particular point in time during our algorithm. And to reflect these over and under consumptions, what we will first do is we're going to update the average remaining resource capacities within the market, as we have 98 units of good 1 and 99 remaining users, 100 units of good 2 and 99 remaining users. And then what we will do as a next step to set the price for the next user, we will again solve our certainty equivalent problem, but which now relies on these updated average remaining resource capacity vectors that we've updated here, which will essentially help us modulate the price up or down, depending on whether the resources have been over or under consumed at any given point in time during the algorithm. Okay, so this simple pictorial depiction of how the algorithm will work can actually be formalized with this algorithmic environment that we have here. And essentially, the algorithm will proceed in 2 phases, a price setting phase where we solve these certainty equivalent problems, and a user consumption phase where users will consume their utility maximizing bundle of goods given the set prices, following which we will update the resource capacities, which will then reinitialize our certainty equivalent problems to update prices for subsequent users. And what we can show about this algorithm is that if we have finitely supported distributions, then this algorithm can actually get us logarithmic regret in the number of users for just a constant constraint violation, which is to say that we can actually significantly improve on the lower bound of square root n for static pricing to just logarithmic regret if we just do the simple tweak to static expected equilibrium pricing, where we're increasing or decreasing the prices of the resources that have been over or under consumed with this procedure that I described to you in the last 2 slides. However, if we look at this algorithm more carefully, we realize 2 key caveats. First, we require access to the distribution of users as utility and budget parameters to set prices at each step by solving the certainty equivalent problems. And secondly, for this guarantee to work, we require that the distribution be finitely supported. However, neither of these 2 assumptions may necessarily be true in practice. And so this really brings me to the final sort of set of results, where I'm going to introduce an algorithm that will be purely based on revealed preferences, which does not require either of these 2 assumptions to necessarily hold true. So the revealed preference algorithm I'm going to introduce, the only data that we're going to need in the setting is going to be sequentially revealed observations of user consumption and nothing else. That is, we're not going to rely on any distributional information, nor the actual realizations of users' utility and budget parameters for this particular algorithm to work. And the only data we're going to use is going to be observations of user consumptions. So here's how the algorithm is going to work, and it can be described by a very natural 4-line procedure. So we'll start by initializing the prices. Then users, each time they arrive, we're going to proceed in 2 phases. So first, they're going to consume their utility maximizing bundle of resources given the prices that they observe. And then we will update our prices. The way we will update our prices will just be the price at the next time step is the price at the previous time step minus a step size times the difference between 2 terms. which corresponds to the difference between the market share of an agent given by D, which is just the total capacity of resources divided by the number of users minus the amount of resources that are consumed. So essentially, what this price update rule is doing is we're increasing the prices of the resources that have been consumed more than their market share and decreasing it otherwise, which is really just operationalizing our intuition from economics 101. Okay. Note that the price update rule only requires knowledge of user consumptions, but no knowledge of the budgets or the utilities or the distribution to be able to update prices within the market. And moreover, if we set the step size of our updates appropriately, what we can show about this algorithm is that it can actually get us square root regret and constraint violation within the system. I'll note that this algorithm is indeed similar to a variety of other primal dual algorithms that have been developed in the literature. However, what I would really like to note is that our algorithm really differs in phase one compared to several of these existing algorithms, in that much of the prior approaches within phase one, they require observing user attributes to be able to make allocation decisions within phase one, and consequently, their phase one takes a very specific functional form. On the other hand, the phase one of our algorithm is a purely posted price step, and which really involves just users consuming the optimal bundle of goods given the set prices rather than just accepting some allocations that are given to them. The other aspect that I'll mention about the algorithm is that this similar algorithmic procedure that we have, we can also apply it for in other contexts, in that it's actually quite general purpose. And in fact, we've also been able to apply it in the context of optimal tolling in the context of transportation networks. Now, let me just make a few quick notes about this regret guarantee that I have at the bottom of the slide. So what I'll note here is that the square root n guarantee that I have here, of course, it's not as good as the logarithmic guarantee I mentioned just a few slides ago, but note that this algorithm applies generally for continuously supported distributions, and moreover does not require knowledge of the distribution for this algorithm to work. The other aspect that you might mention is that we have a lower bound of square root n for static pricing. We have an upper bound of square root n for this algorithm. Is it possible to get a strict separation between the two in terms of a strict improvement of this algorithm relative to static pricing for at least a certain class of distributions? And it turns out that indeed the answer to this question is yes for finitely supported distributions, wherein if we set the step size of our price updates in a more nuanced way with an exploration and an exploitation phase, then in fact we can improve the regret guarantee of the algorithm for finitely supported distributions from square root n to just order n to the 2/5 within the system. So that's pretty much all the regret guarantees that I wanted to mention within this particular talk. Given that I'm a little short on time, I'm going to just skip over this proof sketch and just move to the next sort of part, which is just talking about just the fact that so far I've mainly focused on designing algorithms which allow us to violate the capacity constraints of the resources within the market. However, I'll just briefly mention how we can modify the algorithms such that they're strictly feasible and do not violate the capacity constraints. And in fact, this can be done by a very simple and natural two-step procedure. So in step one, to design feasible versions of the algorithms I've presented, we can just apply the same algorithms as we currently are up till epsilon units of some resource are remaining. And then in step two, we'll just give epsilon over n of the remaining resources to the remaining users within the population. And it's very straightforward to verify that this algorithm is indeed going to result in a feasible outcome. Now, I'll define tau pi to be the stopping time at which we move from step one to step two within this algorithm. And then what we can show about this new feasible algorithm that we have constructed is that the regret of this feasible algorithm can be upper bounded by the sum of two terms, which is just the regret of our original algorithm up to the stopping time tau pi, plus the difference between the number of users and the stopping time up to a logarithmic factor. Okay? And what's nice about this particular general result that I have here on the slide is that we can actually apply this to get the regret guarantees for each of the algorithms I've presented to you, where we allowed some constraint violations to be able to design the feasible algorithms and get their corresponding regret guarantees as well. So in particular, for the adaptive expected equilibrium pricing algorithm, which had just a constant constraint violation, we can show that the feasible version of the algorithm, if I just apply the result on the previous slide, essentially gets the same loss and regret up to constants. That is, we're essentially incurring no additional loss and regret up to constants for that algorithm. On the other hand, for the two reveal preference algorithms that we had, for which we had much higher constraint violations, what we essentially have is that the feasible versions of those algorithms essentially incur the same loss and regret up to just at most a logarithmic factor, which is just to say that essentially the guarantees out here that we got for the setting with constraint violations very naturally extend to the feasible versions of the algorithms with just a little additional loss in the regret up to at most a logarithmic factor that we have here. Okay. So finally, let me just very briefly talk about some numerical experiments that we ran within this work. So I've presented here log-log plots of the regret with the total number of users for the two different reveal preference algorithms that we developed, which are depicted in green and orange out here on this slide for two different data distributions. And we can compare the regret of these two algorithms to a variety of different benchmarks depicted in the other colors. And what you can clearly see here is that our reveal preference algorithms incur significantly lower regret compared to several of these benchmarks, where in fact some of these benchmarks have access to more information on users' utility and budget parameters, such as the distribution or the actual realization of users' utilities and budgets within the market. Okay, so finally, let me just very quickly conclude. So within this work, I studied this online incomplete information variant of Fisher markets. I talked about the limitations of static pricing and introduced two adaptive pricing approaches with improved performance guarantees. And finally, also mentioned to you that we can design feasible versions of the algorithms that I presented without much additional loss in the regret, and also presented some experiments which demonstrated the efficacy of our algorithm relative to several benchmarks. So finally, let me just mention some very quick implications of the results that I've presented. So typical online learning methods often rely on observing user attributes to make allocation decisions. However, within this work, we developed posted price mechanisms wherein utility maximizing agents can just consume their optimal bundle of goods given the prices that are set. And therefore, we're able to somehow enhance the practical viability of typical online learning methods by mimicking how real world markets would typically operate through posted pricing. Secondly, I've hopefully been able to motivate to you the importance of dynamic pricing, wherein static pricing has typically been the status quo when it comes to studying market equilibrium outcomes. However, through our work, we've been able to, I mentioned the limitations of static pricing in the online market context that we studied, and also demonstrated to you that just dynamic pricing with only a very little amount of additional information can help us significantly perform better within this market. And finally, we've been able to overcome some key technical challenges, wherein prior work typically focused on these non-negative and bounded objectives. However, we've been able to extend some of that analysis to the fairness promoting logarithmic objective that we studied within this work. So overall, I'll finally just leave you with this slide, which is just to say that this particular work that I focused on was specifically on the privacy and uncertainty concerns in the context of Fisher markets. But this is, of course, just part of my much broader agenda on exploring sustainability issues in resource allocation, both from a methodological as well as an applied perspective. So thank you so much for your attention, and happy to take any questions.
Thank you. Thank you very much, Devansh. Let's open the stage for questions. Is there any question from the audience? Giuseppe, do you want
I can
to
break the
start?
ice with one.
Yeah.
So first of all, Devansh, great talk. I really appreciate that. Very interesting. I have a question regarding the fairness metrics you considered. So I remember in one case you consider a logarithm in a cost function, and in another case at the beginning of your talk you consider instead of constraint, which I didn't really understand well. Can you expand on that? Can you comment?
Oh, so you're talking about the fairness constraints that I mentioned right at the beginning of the talk?
Yeah, that's right.
Yeah. So let me just go back to it. So yeah, I was not trying to go too much into detail on that part, but maybe I'll just go to the slides somewhere here, I think. Yeah. So essentially within and then I'll just do this. So essentially what this fairness constraint is saying, and again, I didn't exactly define this fairness constraint here, but the way I can describe it to you now. So let's say that the two of us in a transportation network are making exactly the same trip. So same origin, same destination. Okay. This fairness constraint is essentially saying that we're going to bound the ratio of our travel times by some constant beta. Okay, so we're going to take any pair of users that are traveling between the same origin and destination. We're going to compute the maximum ratio of the travel times across all pairs of users, and we're going to bound that by some constant. So that's essentially what this is saying. So yeah, hopefully that clarifies.
Yeah, it does clarify. On the other hand, what about in the Fisher market formulation? You have a logarithm in the cost function, and you
Correct.
mentioned that it sort of enforces fairness. In what sense?
Absolutely. So, yes, exactly. So, in fact, let me, I didn't present the slide very formally. I have this towards the end within the appendix here. So actually, what's very nice about Fisher markets is that essentially this particular logarithmic objective, if we actually just think about it, it's essentially just maximizing the product of utilities because just the log of the product would just be the sum of the logs, right? Now, what's very nice about this product of the utilities is that it actually serves as a very natural compromise between an efficiency promoting objective and a fairness promoting one. So the efficiency relation is just sort of how the geometric mean provides a bound on the arithmetic mean, right? So that's sort of how we get certain nice efficiency properties because the geometric mean just provides a lower bound on the arithmetic mean. So it has some nice robustness properties. But moreover, what's also very nice is that this Nash welfare is actually an objective that satisfies two key properties, that of Pareto efficiency and NV freeness. And again, I've not formally defined what NV freeness and Pareto efficiency are here, but these are essentially two key notions that are often used within the literature to be able to think about what efficiency and fairness typically mean. Right. And of course, the way I motivated fairness within this talk was to say that, well, because we have this logarithmic objective, what that guarantees is that all users will at least obtain some resources in the market, right? If we think of the utilitarian welfare, which is maximizing the sum of the utilities, there could be some users leaving the market with zero utilities, which is absolutely fine within that context. But that is a no-go when we are dealing with a logarithmic objective. So those are at least some ways to think about what fairness properties this particular market has.
That clarifies my question. Thank you.
Okay, yeah, absolutely.
Nice. Thank you, Devansh. And also, this slide, I think, when explained this way, really gives you a good idea of part of the payoff of all of this framework. It's very nice.
Yeah.
Maybe I'll follow up with a question. Have you thought
Mm-hmm.
about the case? This is more future work, right? But have you thought about the case where you have more markets that possibly interact? You could have some properties like that for each market, but maybe they conflict. I'm thinking energy and transportation, or you could think about other things. How would the composition of markets work?
So I guess, Joel, sorry, but like a part of it just cut off. I don't know if it was the
Oh,
internet or so. I'm sorry, I
okay,
missed
okay.
the complete question. Yeah.
So no, I said it's very interesting to see that once you draw the boundaries around a particular market, you have these nice properties. What I was wondering
Mm-hmm.
is there are cases where maybe you have different markets interacting with each other. I'm
Mm-hmm.
thinking as an example, transportation and energy.
Right.
How would the composition of these two different markets work? Or how would something like that be modeled in this framework?
Yeah, no, that's a great question. Yeah, that's something I've not really thought about. But yeah, like you're right in that this at least the framework itself, the classical Fisher market framework, is typically only looking at a single market. And yeah, I think that's a great point. That how do we think about the interactions between multiple markets, because like just the way in this work we studied this like new variant of Fisher markets to somehow better suit certain applications. Similar way, I think that would be another way we could think about it, that what is that new variant of Fisher markets that we might need to develop that might, I guess, deal with the transportation and electricity market interaction. I think that's a great point. Yeah.
Nice, good. We have some work to do.
Right. Yes.
And maybe another question I had, it's just an excuse to give you more space to talk about it, is what are your immediate next steps? What is that you would like to explore next going forward?
Oh, absolutely. So one, I actually have a slide somewhere. Let me just go here. Actually, like one area I'm extremely excited about. So I'll just go here, right? So essentially, especially to extend on some of the work that I just presented today. So one key assumption or limitation that we had within the work was that we assumed the stochasticity of the input, right? And so as a result, we're assuming that all the budgets and utilities are being drawn IID from some distribution. However, of course, if we look at real world data and practice, it's often non-IID and potentially has many possible outliers. And so, in fact, just in terms of the way I think about it moving forward, is that can we extend these posted price mechanisms that we developed in this more stochastic environment to also work well in these potentially non-IID settings that we might typically encounter in practice? And typically, most of the work being done in these non-stochastic settings is largely focused on so-called hidden price mechanisms, because they often rely on observing user attributes. So there's still really this question open, that how do we design these more practical posted price mechanisms within these contexts? So that's really an area that I'm excited about. And I think just going to some of the things that we've also been thinking about recently is that there's also a possibility of maybe augmenting some of these algorithms, maybe with some of these emerging techniques from, let's say, large language models, which really help in capturing such contextual information, for instance, information on outliers, which could possibly help inform some of the design of these mechanisms as well.
Very nice, very nice. Yeah, and by the way, we have to finish that paper about the very last point you
mentioned. Yes. And that is indeed the last point, that we do have some ongoing work in this regard too. Yes.
Yes.
Yeah.
Nice. Very cool. Thank you so much, Devansh. I wish you luck for all the next steps, and
thank you.
It was great to have you here. It's very interesting work.
No, thank you so much. Thank you so much for the invitation. Yeah.
Great. And thank you all for joining. I'll see you next week for the next talk, and also Devansh will share the recording once it's been uploaded.
Sounds great. Thank you.
Take care. Please survive these travel intense days.
Oh, yeah, absolutely. Bye-bye. Thank you so much. Yeah. Bye.